Okay, so we'll start with week 2 session with the tutorial. And I hope the thrust equation for a turbojet engine has been discussed. So you must be familiar with this equation, the thrust that is generated by an engine. This equation is familiar, how it is derived. Have you watched the lectures? Yeah. So I just want you to note. Let me see. Okay. So I just want you to note what is happening here. The thrust depends on the change in the rate of change in the momentum, right? So there is a mass of air which is flowing into the engine. There is mass of air which is flowing out of the engine. So you have m dot E into UE, which is basically the mass flow rate at the exit station and the velocity of the air at the exit station, that is UE. And from that you will subtract m dot I into UI, where I is basically the initial or the inlet station. And then you also have this pressure term. So if you see the pressure term, force is pressure into area. The area that matters is only the exit area. The inlet area does not matter. So this is the more important thing you should know. And optimal thrust is obtained when this term is 0. Okay. So when people design an aircraft, they design it for a particular altitude, and they will design such that the exit pressure altitude is equal to the atmospheric pressure at that particular altitude. So then PE minus PI would be equal to 0 and the thrust would be optimized. Okay. So now if I further just assume that see m dot E is nothing but m dot I plus m dot F, but the amount of fuel that you are adding is very small as compared to the amount of air that you are taking in. So since I know that m dot F is much lesser than m dot I can assume that m dot E is equal to m dot I, and you can write the thrust is approximately m dot into UE minus UI. Now UI is determined by the velocity with which your aircraft is flying, right? So the only way you can change the thrust is by increasing the mass flow rate, that is m dot, or by increasing the exit velocity or the exhaust velocity of the air that you are throwing out. So based on this, we have three types of engines. That is a turbojet engine, turboprop engine, and a turbofan engine. So can any one of you tell me what is the principle behind a turbojet engine? Yeah, please answer. Anyone? Yeah. Right. So in the turbojet engine, what we want to do is increase the exhaust velocity. That is, we increase UE and we don't try to increase the mass flow rate of air that you're taking. So if I just draw a schematic of turbojet here, you have a compressor and a turbine, and then you have a nozzle here. Okay, and there is a combustion chamber. Now for a turboprop engine, it is the opposite thing. So we don't try to increase UE, but instead we try to increase m dot. So what a turboprop engine will do, it has the same structure. There is a compressor, combustion chamber, then a turbine, and you have the nozzle here. But it also has a huge propeller in the front. So what this will do is it will take a lot of air inside. It will extract a lot of air and will throw it into the combustor. So then it is increasing m dot, and by increasing m dot it will increase the thrust. Okay, so the next option is turbofan engine. So turbofan engine is somewhere between turbojet and turboprop. It increases both m dot and the exhaust velocity. So in a turbofan engine, you have a fan sitting inside. So it is always placed inside this diffuser inlet, and then that is connected to a low pressure turbine. Okay, so this is a low pressure turbine which will run the fan, and there is also a high pressure turbine. So that high pressure turbine is going to run the compressor, and there is a combustion chamber. Okay, so this is a multi-spool arrangement, and if you're taking in some m dot here, there will be a cold flow which is m dot c, and there will be some hot flow which goes through the compressor. It undergoes combustion along with the fuel, and then it runs the turbine. So that is m dot h, and the bypass ratio is defined as m dot c by m dot h. So this was a quick revision of your three basic types of engines. Now the question is, how do you define their propulsive efficiency, thermal efficiency, and overall efficiency? So does anyone know the definition of propulsive efficiency? Yeah, please speak up. Right. It is the so the answer that I got is propulsive efficiency is the ratio of the propulsive power to the change in the kinetic energy. So now turbojet is creating some thrust T, and what is power? It is force into velocity, right? So thrust into the velocity with which the aircraft is moving forward. So this is the propulsive power divided by the change in kinetic energy, which would be half m dot E ue square minus half m dot I ui square, right? And what would be the thermal efficiency? What is thermal efficiency? So you are giving some fuel, you're carrying some fuel, you're burning that fuel, you're providing energy. So how much change in kinetic energy is brought about by burning a certain amount of fuel? That is defined by thermal efficiency. So here you will have the change in kinetic energy divided by the energy that you get by burning a certain amount of fuel m dot f, and heat of reaction is qr. So this is the energy. Okay, and overall efficiency, you must be aware, is eta p into eta t. So it is overall propulsive power that you get by burning a certain amount of fuel. So are these definitions clear? Okay. So now what is it for a turboprop? How do you define propulsive efficiency? Again, you have propulsive power, which is thrust into velocity, divided by what is going to be in the denominator? Answers, please. Okay, so go back to your turbo propeller. See, there's something important over here. In a turboprop, maximum of the thrust is generated because of the m dot term, right? And to turn this huge propeller, you will have a shaft, and your engine is going to give power to the shaft, which we call as P shaft. Okay, so uh, now what is efficiency? Efficiency is what do you get for what do you give. So you are getting propulsive power for certain amount of power that you are giving to the shaft. So this is the difference in the definition of propulsive power between turbojet and turboprop. Okay, And similarly, you can define thermal efficiency. So what is thermal efficiency now? It is how much how much shaft power do you get for how much fuel you burn. So here eta T is going to be equal to P shaft divided by m dot F into QR. Is this clear? Okay. And in turbofan, now this is easy. So for turbofan, we have again the thrust which is generated into the velocity with which the aircraft is moving divided by the change in the kinetic energy. So remember, the change in kinetic energy is going to be different here. You have m dot C, which was coming in with some velocity u inlet. M dot H was also coming in with some velocity u inlet. But after going through the engine, m dot C is coming out with a velocity of UEC. So the cold flow has a different exhaust velocity and the hot flow has a different exhaust velocity. So then you will calculate the change in kinetic energy accordingly for the cold flow and hot flow separately, add them together, and that will come in your denominator. Okay, and again thermal efficiency can be defined similarly. So next we'll move on to ramjets and scramjets. So what are the differences between a ramjet and a scramjet, or what is a ramjet? What is ramming effect? Okay, in ramjet, the combustion takes place at subsonic speeds. In scramjet, the combustion takes place at supersonic speeds. So that is the main difference between them. How is a ramjet different from a turbojet? So you can see here, in the ramjet, we don't have any compressor, turbine, we don't have any turbo machineries. And so we understood that we need to do compression because combustion has to happen at slower speeds. It cannot happen at very fast speeds. So you have to compress the air, bring it to slower speeds and increase its pressure. So that is achieved by creating a series of oblique shocks. And this mechanism of reducing the pressure, increasing the pressure using oblique shocks is called the ramming effect. Is that clear? Yeah, and as one of you answered, ramjet and scramjet, they are different because in a ramjet, we create oblique shocks in a manner such that by the time your flow reaches the position where combustion is going to happen, there the flow becomes subsonic. So ramjet and scramjet both are operating at supersonic speeds, that is Mach more than 1. But in the combustion chamber, for ramjet, Mach becomes less than 1. But for a scramjet in the combustion chamber also, Mach is more than 1. And which is why scramjet is much more difficult to design, and also testing of a scramjet is very difficult because flame cannot be stabilized at such high speeds. So this is still open research topic, right? Now, what happens is that, as I said, when an aerospace engineer designs a particular engine, they design it for certain conditions. For example, you can design a ramjet to operate at, say, 30,000 feet maybe. Okay. So at 30,000 feet, the pressure is going to be different. At 10,000 feet, the pressure is going to be different. So now the question is, if I have designed this particular engine for a particular altitude, what happens if you allow it to operate at different altitudes? The operating conditions become different because the atmospheric pressure that it is able to see is different, right? So for example, let us say you designed your ramjet such that oblique shocks are created, and in a ramjet you'll always have these very pointed inlets. So for example, here you have this wedge, then you also have a pointed inlet over here. So in the design condition, there will be most optimum shock reflection so that the series of shocks ensure uh, pressure is increasing with minimum stagnation pressure losses. But if you operate at different altitudes, there may be conditions where the oblique shock does not touch the lip of the inlet, and this is called the subcritical inlet condition. Whereas in another condition, the oblique shock may end up reflecting much more inside of it does not touch the lip, but it goes much more inside of your design, and then this is called the supercritical operation condition. And in both of these cases, the losses in the stagnation pressure will be much more as compared to what is the stagnation pressure loss in the design condition. Is this understood? These three inlet conditions in a ramjet? Okay. Okay, so now let us go for some questions. These questions are from my end. I will discuss some questions also from the previous assignments, but first we'll go through these questions. So, uh, can you give me a comparison of the propulsive efficiency? We just discussed the definitions. Propulsive efficiency of different types of engines. And the options for you are turbojet. Okay, then turbo fan is there. You have a turboprop. Then you have scramjet and ramjet. So for all these engines, please tell me whose propulsive efficiency is going to be the highest or lowest and so on. Right. So the answer given here is turboprop more than turbofan, more than turbojet, more than ramjet, and more than scramjet. Okay. Okay, so the next question is compare the maximum speeds that can be achieved by these engines. Okay, so we know scramjet flies at very high Mach numbers. Mach number is almost like it's more than 5, right? And for ramjet, the Mach numbers are like somewhere between uh, 1 and 4 actually. Okay, then we have turbojet, and then turbofan, and then turboprop. So what is the reason here why turboprop engines cannot fly at very high speeds? Right. So when you're flying at very high speeds, remember what is the speed that the tip is going to see? It is going to see a relative velocity, and if you are flying at very high speeds, then the speed at the tip is going to be the highest. And if that exceeds the sonic speed, if you get supersonic speeds here, then shocks can occur, and that will cause losses. So that's why turboprops cannot be operated at very high velocities. Okay, so now compare the TSFC. So what is TSFC? Thrust specific fuel consumption. What is the definition of TSFC? So it is how much fuel you are consuming, right? That is m dot f, but specific to thrust, how much thrust you are producing. This can also be written as m dot f divided by m dot a upon thrust divided by m dot a, right? Which is nothing but fuel by T by m dot a, which is what? It is the specific thrust. Okay, so now what is the TSFC for these different engines? Compare the fuel consumption for these different engines. So what will be the lowest? Remember we were talking about thrust. Thrust goes as m dot into ue minus ui. So in turboprop, how are you increasing thrust? You are increasing by increasing the inlet mass flow rate. Correct. And to increase the exhaust velocity, you need to raise the temperature in the combustor by a lot. So if you are increasing UE, then your fuel consumption is going to be higher. If you are increasing m dot, the fuel consumption is going to be lower, right? So what is TSFC trend going to be? It is going to be least for turboprop, then turbofan, then turbojet. Okay, what about ramjet and scramjet? After turbojet? Yeah. Okay. Someone is saying that ramjet is lower than turboprop. Someone is saying that ramjet is more than even turbojet. So what is it? Yeah. Which one is it? Where should I place the ramjet in this particular answer? After turbojet. Okay. Why? So this is wrong, and this is right. Why? What is the reason? See, you are basically going to conduct. You are going to let the combustion happen at very high pressures in ramjet. Even if it is in subsonic regime, it is going to be at very high pressures. And even if it is subsonic, it is not in turbojet. It would be like Mach would be around zero point 0.1 in the combustion chamber, but in ramjet it is not going to be 0.1. It's going to be 0.6, 0.7, something like that. So when the combustion occurs at much higher speeds and much higher pressures, then to raise the temperature you need even more fuel. And for the same reason, scramjet's fuel consumption is going to be even higher than ramjet. Is the reason understood? Okay, I'll assume that the answer was yes. I couldn't hear anything. Okay, so let us compare now the specific thrust. So I just told what is specific thrust. Specific thrust is nothing but the thrust you produce by m dot. So first, let us define the specific thrust for a turbofan. For a turbofan, specific thrust will be thrust divided by m dot h, because in the engine it is this m dot h which is going through the combustion chamber. Okay, if I were to use T divided by m dot C plus m dot h, then the answer would be a little different. So right now let us assume that we are comparing for m dot h, because if you have to compare a turbojet and a turbofan, for a turbojet the entire m dot goes uh, undergoes combustion along with m dot f, right? But in a turbofan you have m dot C and m dot h, and only m dot h is going to go through the combustion part. So now can you tell what is the comparison for specific thrust for a turbojet and turbofan? Sorry, I couldn't hear you. Turbofan is higher, right? So for turbofan being higher than turbojet, the definition of specific thrust we have used is this one. Okay, but if I were to use the other definition, if I was to use this definition for specific thrust, then remember that turbojet produces more specific thrust than turbofan. Okay, is this clear? For the simple reason that here you have more m dot because of the cold flow. Okay, so we'll move on to the next part. So in the last tutorial session, I discussed about static and stagnation quantities. I hope you went back and looked at it. So here we talk about static conditions, which are the actual conditions that you would measure in a particular flow, like pressure, temperature, density. And if we bring this flow to a stop through an imaginary isentropic process, then the state that we get is the stagnation quantity. Okay, and this is usually used for a reference. Like if I have to compare two flows, right? So for comparing flows, we need a particular reference, and the reference is usually the stagnation quantities. And we derived this equation. We started with the gas dynamic relation that we know, that stagnation enthalpy is equal to static enthalpy plus v square by 2. And in the last session we derived this equation, the relation between the stagnation temperature and the static temperature. So you guys can refer these books, Zucker and Biblar's, or the book on compressible flows by Anderson, for looking into the gas dynamic relations. And if you know T naught by T, and you know the adiabatic relations such as PV per gamma is constant, and then you have the TV relation, PT relation. So from there you can get the P naught by P, T naught by T, rho naught by rho. All these gas dynamic relations you can easily obtain. So I'll not be deriving these. If there are any doubts, maybe we can discuss it in the next session. Is that okay? Okay, now we'll discuss these components of a turbojet engine again very quickly. So at the inlet, you have these atmospheric conditions. The atmospheric condition is going to be equal to the stagnation pressure of the inlet. Okay, and then in the diffuser, the flow is going to get compressed. But remember, no work is being added in the diffuser. In the compressor, there are rotors and rotor stator combinations. There are fans that are going to basically rotate the flow. It is going to add work to the flow. So here in the compressor, work is added. Okay, in the combustion chamber, heat is added. And in the turbine, work is produced. But in diffuser, there is neither work added nor heat added, and in the same in nozzle. Okay, so now let us see the variation of the static pressure and the stagnation pressure along the axis of this turbojet engine. So basically what I'm asking is, how does the pressure change as the air, the fluid moves from the diffuser to the compressor, then to the combustion chamber, then to the turbine, then to the nozzle, and so on. Okay. So you remember the Brayton cycle. Okay, so now let us answer these questions. So I'll just draw call this diffuser, compressor, then combustion chamber, turbine, and nozzle. So what will happen to, let us start with the easy thing, stagnation pressure. So what is going to happen to the stagnation pressure in the diffuser? Yeah, I can't hear. Please speak up. No, the stagnation pressure. See, yeah, the flow is getting compressed, so the static pressure will increase, but the stagnation pressure will not change. Stagnation pressure will change only when there is any work or heat added to the system or subtracted from the system, right? Okay, yeah. So stagnation pressure is going to remain constant in the diffuser, but in the compressor, remember, work was being added, so then the stagnation pressure is going to increase. And then in the combustion chamber, what will happen? In the combustion chamber, it is by assumption that the static pressure and the stagnation pressure remain constant. So this is an assumption. In reality, it reduces slightly, and my drawing is automatically doing that. So it's supposed to remain constant. And then in the turbine, work is being extracted. So now what will happen to the stagnation pressure? Yeah, it will decrease. Until where will it decrease? Will it become lesser than what it was earlier, or what is going to happen? Will it remain same? So remember, in the exit condition PE is equal to PA, and that is equal to P naught 1, which was in the diffuser, right? And this is also going to be equal to P naught E. So then, wow. Okay, so then what is going to happen is the stagnation pressure is going to come back to the same value as it was in the inlet condition. So in the turbine it reduces, and in nozzle it remains the same. No, that will not mean so. How do you find the exit velocity? So we are talking about stagnation pressure. Remember, does the stagnation pressure come in the calculation of your velocity? Yeah, so which ratio is going to come in the formula? It will be the turbine to the nozzle, right? Not, yeah, not from P naught 1 to P naught E, that's not going to come. It's going to be, if you refer to the stations that I have drawn above, yeah, the ratio that will matter is P naught, P naught 3 by P naught 2, that is the compressor pressure ratio, and P naught 5 by P naught 4, which is the pressure ratio across the turbine. And that you can compare. So P naught 5 is basically equal to P naught E. That is what I'm saying. So the pressure ratio will be from the exit and from the inlet of the turbine. That is the pressure ratio that will matter. Okay. Okay, I'll take that as it. Yeah. Stagnation pressure of the inlet of the entire engine. Yeah, yeah. So, okay, so if the outside static pressure is P atmosphere, and you are sending the exhaust and at exit pressure PE, and what you are saying is PE is equal to PA, right? So won't P naught E be equal to P naught A? No, but there is a difference. There is a difference in the T naughts. So when we plot the stagnation temperatures, that will turn out to be different. Okay? Yeah. So now we'll just plot, that will come in the next plot, but let me first do the static pressure. So static pressure is going to increase in the diffuser, like it was answered earlier, but the increase is going to be small in the diffuser. In a compressor, the increase is going to be much higher. And then in the combustion chamber, it remains almost same. Then the static pressure decreases in the turbine, and then further decreases in the nozzle. And like just now mentioned by one of you, as you said, the exhaust pressure should be equal to the ambient pressure. That is the usual operating condition. Okay, so now we'll go ahead with the stagnation temperature plots. So what is going to happen in the diffuser? What will happen to the stagnation temperature? Any answer? Right. So I'll do one thing. I'll use the same color for static quantity. So the stagnation temperature remains the same. Oh, sorry, stagnation temperature remains the same. Sorry, in the diffuser. In the compressor, it will increase. So if you remember your Brayton cycle, the TS plots, because you're adding work, the stagnation temperature is going to increase. Okay, bad planning. Don't. What about in the combustion chamber? What will happen to the stagnation temperature? It will increase even further, right? So it's going to increase all the way. And then in the turbine, it's going to decrease. So how much decrease is it going to be? Will it come back so that the stagnation, so we know that in the nozzle stagnation temperature is going to remain same. So will T naught drop up till this value, or will it be much higher? Well, it will be much higher because your exhaust velocity is different, right? So the drop of stagnation temperature in the turbine will not be so much, and then in the nozzle it's going to remain same. So there's a lot of difference in the inlet stagnation temperature and the exit stagnation temperature. Is this clear? Okay, so now we'll quickly draw for static temperature. So what happens to static temperature in the diffuser? Yeah, it will increase slightly. Okay, then again it will increase in the compressor. There is a very sharp increase in the combustion chamber when you draw for static temperature. Okay. It shouldn't go higher than the stagnation temperature, just you should note that, because always your static quantity is going to be smaller than the stagnation quantity. And now if you see, I have brought the static quantity very close to the stagnation quantity because the flow velocity becomes very small inside the combustion chamber, and then the temperature will start to drop in the turbine. Okay, excuse me. And then it will further drop in the nozzle. But again, you should note that the inlet temperature and the exit temperature are very different. The exit temperature will be much higher than the inlet temperature. I hope these two graphs are clear, stagnation temperature and static temperature. Are these graphs clear? Okay, so the next thing is density, stagnation density and static density. So what happens to stagnation density? Okay, so that P is equal to rho RT also holds for stagnation quantities. That is, P naught is equal to R naught. What is this? Yeah, rho naught. So what's going to happen to rho naught in the diffuser? P naught is not changing, T naught is not changing, so rho naught will not be changing, right? Stagnation density is going to remain same. What will happen in the compressor? Answer. Am I still audible? Okay guys, what will happen to the, yeah, it will increase, right? So it will increase because after all you're doing compression. So what will happen in the combustion chamber? Now please understand, In the combustion chamber, T naught is increasing. P naught remains almost same. So rho naught must decrease. Okay. And then in the turbine, it will further decrease. Will further decrease. And oh, okay, I don't know why it's not coming. And then in the nozzle, it will remain the same. So now if you see, I have drawn the stagnation densities. I have not drawn them equal. So whether it will be equal or not, that depends on your operating condition. So that is not very clear. But there is some clarity for your static density. So we'll see how static density changes. In the diffuser, it will increase slightly because again there is some amount of compression happening here. In the compressor, the static density will increase much higher. Then in the combustion chamber, it will decrease. In the turbine, it will decrease further. And then in the nozzle, it will decrease even further. And the static density at the exit will be lesser than the static density at the inlet. Now the reason is that, see, we try to achieve this particular condition because in combustion we prefer that the molecular weight of the products is lesser than the molecular weight of the reactants. Now this is an important point, very important point in rockets, not so important in turbo machineries, but it is something worth remembering. Okay. Is this clear? Should I move on? Can you guys speak loudly? I really cannot hear you. Yeah, okay, thanks. Okay, so now here are some questions from the previous assignment, and they're very easy, so I hope all of you will answer them very quickly. We've discussed this earlier. So in gas turbine, combustion takes place by what type of process? Isobaric, right. So I'll just highlight the right answer. Okay. Then question 2, in closed cycle based gas turbine, the maximum cycle temperature is limited due to what? Is it the combustion chamber, that is boiler, or is it the turbine or the compressor? Turbine. Okay, why the turbine? What in the turbine? Right, right. The material can, exactly. So it is a material constraint. It is not a design constraint. That is something worth remembering. Okay, multi-stage compressors are desirable for which of these following? Okay, compressors, do they increase work output? No. Do they do any heat transfer? No. Reducing work input to the cycle? No. So it's raising pressure ratio of the cycle. Okay. Alright, adding exhaust heat exchanger to a simple ideal gas turbine cycle would improve efficiency. Fine. Okay, then advantage of using twin shaft arrangement of turbines is to, so why do we use twin shaft arrangement of turbines? Where do we use this twin shaft arrangement? Yeah, for example, in a turboprop or a turbo shaft. Yeah, so what is the answer? Sorry, I cannot hear you very clearly. Option 1, 2, 3, 4. Which one? Well, that's not the answer. The answer given here is to increase the work output. So what you are talking about is the multi-spool arrangement, and what they've given here is the twin shaft arrangement. So, what is a twin shaft arrangement? So, as much as I know, it is like you have these multi-spool is where you have a shaft coming from inside which goes up till the propeller, and the outer shaft that will run the compressor or something. Okay, maybe I'll check this and get back to you next time. So the answer here is to increase the work output. Right, which among the following engine is suitable for low altitude and low flight speeds? Piston prop, right. Okay, a related question would be, why do turboprop engines fly at lower altitudes? Can you fly turboprop engines at higher altitudes? Okay, why? Right. So as you increase the altitude, the density, ambient density decreases. So m dot decreases, and hence the thrust also decreases for a turboprop. Okay. Thank you. Then question 7. How does the propulsive efficiency vary with increasing flight speed for a turboprop engine? So if I increase the velocity, m dot is going to increase, right? Thrust is going to increase. So propulsive efficiency should. What is the answer? Correct. It should first increase, then decrease. So uh, it's very obvious why it will increase, because as you increase m dot, as you increase the speed, m dot is increasing, thrust is increasing, so your efficiency is going to increase. But after a certain flight speed, we discussed that there will be problem of shocks occurring at the tip of the turboprop, which is why eta p will decrease. Okay, so the answer here is first increase and then decrease. Okay, so what about question 8? Propulsive efficiency of the aircraft is defined as, we discussed this already. So option 3, thrust power to change in kinetic energy, right? Okay. The working fluid flowing through a turbine remains in a single phase, has two phases, three phases, it's a mixture. Huh? Okay, what is a phase? Uh, yeah, it remains in single phase. So what is a phase? Phase is whether it is solid or liquid or gas, right? So what happens in a turbine? It's always in the gaseous phase, right? So the answer is remains in single phase. Okay. Then choose the incorrect sentence from the following for a turboprop engine. Majority of the engine thrust is produced from the propeller. True or false? True. Okay, so this is true. You have to choose the incorrect one. Turboprop engines. Yeah, second one is incorrect. Okay, so that gives us the answer. Yeah, so multiple spool arrangement will be used in these engines. That is right. It is used for low altitude flight applications. Just now we discussed. All right, question 11. In general, the overall efficiency of a gas turbine is lower or higher than a reciprocating engine. So, you know what is a reciprocating engine? It's a piston engine. overall efficiency of a gas turbine engine. So what is overall efficiency? Okay, just tell me one word answer for the first part. Is it lower or higher? What is the answer here? Lower, right. Why? There's no high velocity inside the combustion chamber. Okay. Okay, see, the most important point is that you should attain a very high temperature after combustion. Okay, so the temperature after combustion that you obtain, that matters. So because that, let us say that is the temperature in at the inlet of the turbine. Okay, so this temperature, from there you are going to exhaust it to the exit temperature. The larger this difference, the more the energy that you are going to, or the more the work that you are going to produce. So if you attain very high temperatures and also high pressures, so in a gas turbine, the pressure at which you operate is higher, but the temperatures that you can achieve in gas turbine are lower than that in a piston engine. So the answer here is both, for both the blanks, it is lower and lower. Okay, is this clear? Okay. Yeah, so I think that's all the questions I have for today. Do you guys have any questions to ask? We just have a minute more actually. Any questions? Okay, so I have a question before leaving, so that next time you all will give me the answer. So the question is, what happens if I inject water in in a turbojet engine in the compressor stage? Or what happens if I inject it in the combustor stage? Well, usually what we inject is water plus methanol. Okay, so go and read about this or think about this. If you like, you can try and answer it right now. What will happen if you inject water? The compressor, yeah. Compressor blades, do they have any heat? I mean, are they subjected to very high temperatures? Slight. You know, there is this condition that when you're flying at very high altitudes, sometimes there is frosting. The temperatures are so low in the compressor that the water vapor in the surroundings can, when they get into contact with this metal of the compressor blades, it actually starts frosting on the blades. So even if there is slight increase in the temperature, it is not so much. As a matter of fact, that's why we add methanol. So if we are injecting water into the compressor, the temperatures are so low at high altitudes that the water will start condensing on the blades, and that will change the shape of the blades, and that will change the efficiency of your compressor. So that answer doesn't work. So what will happen? Okay, think about this. Why would someone want to inject water uh, so we are having this methanol to reduce the freezing point of water. That is why this mixture is injected. But why would you want to inject water in the first place? So that is the question. Okay. Efficiency increases. How? Yeah, efficiency increases, work output increases, but how? Yeah, it is one of the thrust augmentation method as you are pointing out. So I'll write this word here, but I have not got a satisfactory argument yet. Okay, so I'll do one thing. I'll end the session right now, and I will explain this concept in the next session, and maybe you guys can think about it. Think in terms of how will the thrust change, why will the thrust change, and also go back to your TS diagrams. So you have these TS diagrams where you have basically the Brayton cycle, right? So how is this Brayton cycle going to be affected by this water methanol injection? Okay. Any other doubts, any questions that you have that you want me to uh, talk about in the next class? So if you tell me beforehand, maybe I can prepare and get back to you. Heat exchanger. Okay, let me go back. Yeah. No, it's not question 5. Question 4. Okay. So adding exhaust heat exchanger to a simple ideal gas turbine cycle would improve the efficiency. So you are adding a heat exchanger to the exhaust, right? And at the exhaust, you like we discussed, the temperature of the exit is much higher. So TE is very high. But I also said that T04, say that is the inlet temperature, inlet stagnation temperature of the turbine. So from T04 to TE, that change determines what is your exhaust velocity. So now if you add a heat exchanger at the exhaust and you reduce TE further, then your UE is going to increase, isn't it? Does that make sense? Yeah, yeah. So that will, yeah, it will improve your efficiency. It will not improve work output. Okay, it will not improve work output. It will only improve the efficiency because it will improve your thrust. Work output is what the turbine is producing. That will be used to run the compressor. And efficiency will be defined in terms of thrust into the velocity. So the thrust component, that part is going to increase because of this adding the heat exchanger. Okay. Okay. Okay, so I'll just stop recording now.